Every year, powerful earthquakes shake our planet, cracking roads, toppling homes, and destroying infrastructure. Yet, standing tall in the midst of chaos are towering skyscrapers, seemingly unaffected giants of concrete and steel. How do these monumental structures survive what entire cities cannot? What secrets lie in the steel skeletons, the foundations, and the sway of these architectural marvels? Today, we're diving deep into the engineering genius behind skyscrapers and how they're built to dance with the earth, not fall to it. This is not just about concrete and bolts. This is a story of brilliant innovation, failure, resilience, and human ingenuity. Let's explore how skyscrapers stay standing when the earth beneath them roars. To understand skyscraper resilience, we first need to understand the enemy, earthquakes. Earthquakes occur when tectonic plates shift along faults, releasing vast amounts of energy. This energy travels as seismic waves through the ground, causing violent shaking. Unlike wind, which pushes a building from the side, earthquakes move the ground itself, often in multiple directions simultaneously. The base of a building is yanked, while the top tries to stay in place. This results in intense shearing forces. These aren't just side-to-side shakes. They're up and down, diagonal, twisting motions. The taller the building, the more severe the impact, unless it's been engineered to handle it. When people think of skyscrapers, they imagine solid, immovable structures. But in earthquake engineering, rigidity is a weakness. The secret? Flexibility. Engineers design skyscrapers to bend and sway, not break. This is called ductility, the ability of materials to undergo significant deformation without failing. Steel, used in most high-rise frames, is incredibly ductile. Unlike brittle materials like concrete or masonry, steel can absorb energy by stretching and returning to shape. Modern skyscrapers are designed like vertical cantilevers, flexible poles that move with the motion rather than resisting it outright. Their swaying might be terrifying to experience, but it's actually what keeps them intact. What you see above ground is only half the story. The real battle against earthquakes often starts below the surface. Skyscrapers are anchored with deep foundations, either piles or caissons, extending tens of meters into stable soil or bedrock. This helps spread the seismic forces across a larger area and reduces the chances of uneven shaking or soil liquefaction, where the ground behaves like a liquid. In seismic zones, engineers go further, designing foundations that allow some movement without causing structural failure. Some even include base isolation systems, which we'll cover shortly. In essence, the taller the tower, the deeper the roots. Every skyscraper has a hidden skeleton, a carefully designed internal structure that gives it strength and flexibility. The most common design systems include moment-resisting frames, steel frames with rigid joints that allow the building to sway without collapsing. Shear walls, vertical walls often of reinforced concrete designed to resist lateral forces. Bays, braced frames, steel beams arranged in diagonal patterns to distribute loads. Tiatu, core and outrigger systems, where a central reinforced core connects to perimeter columns through horizontal outriggers, creating a stiff but flexible structure. Each component is strategically placed to absorb and redirect the seismic energy, keeping the building upright and safe. One of the most revolutionary technologies in earthquake engineering is base isolation. Instead of fixing a building rigidly to the ground, base isolation allows it to float literally. Rubber bearings, sliding pads, or spring systems are placed between the building and its foundation. During an earthquake, the isolation layer absorbs most of the movement, reducing the force transmitted to the structure above. This is especially effective for mid-rise structures and critical buildings like hospitals, data centers, and museums. Some skyscrapers now include hybrid systems, combining base isolation with energy dissipation devices like dampers. Speaking of which, ever noticed how cars have shock absorbers to smooth out bumps? Skyscrapers have them too, on a much larger scale. Tuned mass dampers are giant suspended weights, sometimes hundreds of tons, placed near the top of tall buildings. They sway opposite to the building's motion, absorbing energy and stabilizing movement. A famous example? The Taipei 101 Tower in Taiwan. Its 660-ton damper is a gold sphere suspended inside the tower, moving in harmony with seismic and wind forces. Other types include viscous dampers, using fluids to absorb energy, and friction dampers, relying on sliding surfaces. Yielding dampers, using the plastic deformation of metals to dissipate energy. These systems reduce stress on the building's core and make the ride a lot smoother during a quake. Engineering isn't just about design, it's about learning from failure. Past disasters have shaped the codes and practices we follow today. The 1985 Mexico City earthquake. The 1995 Kobe quake in Japan. The 2010 Haiti disaster. The 2011 Great East Japan earthquake. Each catastrophe taught engineers something new: how different soils respond, how resonance affects building heights, and how crucial redundancy is in structure. As a result, seismic building codes around the world have become increasingly sophisticated, especially in regions like Japan, California, Chile, and New Zealand. These codes mandate structural analyses, material strengths, design reviews, and regular retrofitting. They don't guarantee perfection, but they significantly improve survival chances. A design is only as good as its execution. Many buildings collapse not because of bad engineering, but because of poor construction, corruption, or lack of maintenance. Skyscrapers that survive earthquakes often do so because the engineers, contractors, and city officials followed every guideline, used the right materials, tested everything, and inspected every bolt. In contrast, even well-designed buildings can fail if corners are cut. Earthquake resilience is not just an engineering issue, it's a societal one. Skyscrapers don't resist earthquakes by fighting them. They survive by moving with them, flexing like trees in the wind, absorbing energy like springs, and anchoring deep like mountains. It's a brilliant blend of science, art, and human ambition. In a world where natural disasters will only grow more frequent, our cities must become smarter, safer, and more resilient. So next time you look up at a towering skyscraper, remember, it's not just a symbol of power, it's a triumph of engineering, designed to move, sway, and survive. And that is why skyscrapers stay standing when the earth shakes.